Welcome to today's webcast brought to you by Industrial Laser Solutions and sponsored by SPI Lasers. I'm David Belforti, Editor-in-Chief of Industrial Laser Solutions, your host for this, the 27th in a series of webcasts designed to advance industrial laser awareness of the technology benefits of this product for laser materials processing. Today's event is a very timely subject, welding with nanosecond pulse fiber lasers, which will be presented by Dr. Jack Gabstol, Vice President of Pulse Business Line for SPI Lasers. Before we begin, I want to cover a few housekeeping items. At the bottom of your audience console are multiple application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your questions. We will try to answer these questions during the live Q&A portion at the end of this webcast. You can expand the slide area by clicking on the maximize icon on the top right of the slide area or by dragging the bottom right corner to enlarge. In fact, you can expand and reposition many of the components on your screen. So please feel free to arrange as you desire to give you the optimal webcast viewing experience. If you have any technical difficulty during the webcast, please click on the Help widget. It has a question mark icon and address common technical issues. If you still need assistance, just type your issue into the Q&A widget, and a member of our webcast support team will work with you to correct the problem. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage at www.industriallasers.com. Now it gives me great pleasure to introduce Dr. Jack Gabstol, Vice President of the Pulse Business Line at SPI Lasers. Jack has expert knowledge in industrial laser technology with more than 30 years of industrial laser material processing experience. He is widely published with over 50 technical conference papers and articles and has given a number of technology-based webinars, including earlier ones with ILS. Jack has a degree in metallurgy and material science and obtained a PhD in laser materials processing from Imperial College London, focusing on developments in laser processing. Jack is actively involved in wider promotion of industrial lasers, being chair of the UK Make It With Laser program, and as a member of the Association of Industrial Laser Users, for which he is chair of the AILU Special Interest Group for Micro and Nano Laser Processing. Jack, we are all looking forward to your presentation. The floor is now yours.
Great. Thank you very much, David, for that introduction. Yes, I'm very pleased that you've taken the time out to listen to me for the next hour on something that I hope will be of interest and also will prove to be novel in terms of its content. And that is basically welding with nanosecond pulsed fiber lasers. The things that we want to try and cover is a little bit about, who we are, SPI. We just need to put that into context. A little bit about fiber lasers and what benefits these kind of products do. As you probably are aware, with an audience, an open audience, we have to assume that not everyone is laser savvy or even fiber savvy. So we need to make sure we can bring people up to speed very, very quickly. Then what I'd like to make sure that we do is we kind of explain what these nanosecond type fiber lasers are, and in particular the benefits of what we call MOPA design. Because many people that are involved in welding tend to consider mainly conventional welding or lasers for welding. And these tend to behave slightly differently, so we want to try and make sure we get that across. We'll deal with some of the challenges of welding and also why nanosecond pulses could work in this particular application. In terms of the applications themselves, what I'd like to do is cover the whole broad spectrum of welding opportunities, or welding and joining opportunities with this kind of technology, basically from plastics to dissimilar metals, and also perhaps stress some of the multi-process capabilities that these lasers have. After all, they are best known for their micro-machining and marking capabilities. And finally, we'll summarize the topic areas. A very quick summary of who we are. SPI Lasers is a manufacturer of fiber lasers based in the UK, and we basically make our own fiber. We're pretty much vertically integrated in most regards, and we have a global service and sales presence. We're very much involved in macro, micro, and marking applications, and pride ourselves on our applications know-how and expertise. In terms of our company history, just to put things into perspective, we are quite a relatively young company, formed effectively in 1999. But basically, we were originally a telecoms company that refocused into the industrial laser arena and decided to make fiber lasers just over 10 years ago, about 13 years ago. So basically, we have been manufacturing fiber lasers, for industrial fiber lasers, for over 10 years, about 12 now. We were acquired by Trumpf in 2008, but run autonomously and independently from Trumpf. And more recently, we have acquired JK Lasers, that is now part of the SPI family. In terms of products, we have everything from, on the left here you'll see our pulsed fiber G4 products. We have then a whole host of CW products from 200 watts up to about 4 kilowatts. And those are the kinds of lasers that are more commonly known for their welding applications. So, I guess, that's the kind of preamble, just to give you a bit of flavor for who we are. And now on to the bulk, in terms of joining materials. Basically, joining of materials is fundamental to manufacturing. It is one of the key processes that enables us to make things. And in fact, if we think about it, joining metallic materials is basically quite an old technology. And actually, welding dates back to 1885, with basically the invention of the electric arc. And that's basically, before that, it was all forging. But that was when true welding basically came onto the scene. And key to this was effectively the development of local heating capability, and with that, the electric arc. I think it was Bernardos and Olszewski, I think, if I recall from my metallurgical background. But the advent of laser technology in the 1960s produced effectively the perfect heat source. And that is what lasers are. Lasers are a very controllable heat source, a focusable heat source that you can turn on and off at will, and direct to the point of use. And that's what makes them so useful for a whole host of materials processing applications, but also, more importantly, for the joining of materials. Here we're talking about the importance of being able to generate high intensities. That's basically the high energy and high watts per square centimeters, high energy densities that are required to melt materials. We require high levels of stability because we basically want to have consistency in joints in the welding process. And also the controllability, being able to basically, as I said, switch on and off at will. And in terms of conventional laser welding, most people are aware that CW lasers have been used for this kind of application for many, many years, since the invention of lasers, pretty much. Since the late 60s, these lasers have been welding. But also in the use of what I would call millisecond pulse laser sources. whether they are CO2 or more conventional solid state, and previously that was Nd:YAG at 1 micron. Those kind of technologies have been around for 50 years, and they have been providing welding solutions for industry. However, more recently, the advent of fiber technology has brought on a new era in terms of the opportunities and the capabilities and accessibility of welding technology. In terms of the types of lasers being used, as I said, the basic type of laser is a CW laser or a continuous wave laser, where basically laser is measured by the power. And here you can actually see the top graph that shows that basically you get a stable output over time, and you can turn that on and off, and that basically you do by modulation. So you can actually turn the laser on and off very rapidly, very controllably, to give energy to the workpiece at the point and time that you want. More recently and more interestingly, perhaps the QCW type lasers, where these lasers are able to produce, for example, millisecond pulses with higher peak powers at reduced average powers than their continuous duty operation. So basically this gives us the ability to overcome material thresholds and punch in larger amounts of energy to create molten or larger molten pools that then resolidify to form pulsed type welds. In some respects, some of the shorter pulse lasers are similar to that, but in fact what we see is even higher levels of peak powers with lower average powers. And that basically causes us a few challenges, because really we need to balance those out in order to be able to weld. So why fiber? Why is the fiber revolution rolling over the industrial landscape in terms of materials processing and welding? Well, it basically emits very close to the Nd:YAG or solid state wavelength at 1 micron, which is basically ideally suited to absorption by metallic materials or many metallic materials. We're able to tailor beam sources to generate high brightness or flat beam profiles through fiber and mode selection. So it basically gives you a lot of flexibility. These lasers offer high wall plug efficiency, reducing electrical and cooling requirements, and basically the complexity of integration. So they're basically relatively easy to integrate into systems for generating processes, industrial processes. They're sealed, flexible, require minimal space. There's very few internal free optics. It's all one piece effectively. And so are very adaptable in being able to deliver the energy to the workpiece, particularly through fiber delivery. And they offer the best stability in power, temporal beam response, and spatial profile mode for industrial lasers. And I guess, if you follow the industrial revolution effectively, you'll see that the fiber lasers are the new kids on the block, well, 10 years now, but have really commanded a leading market position and adoption within industrial processes. In terms of the types of lasers that I want to talk about today, we're going to talk about relatively low power lasers, and it's the little red sort of dotted circle. We want to talk about low powers, typically under 100 watts of average power. So it's not the big, solid, thick welds. We're going to deal with something that's slightly smaller. And in terms of the challenges that we have for joining, again, the most important thing is the ability to control heat input. And I think that's why the lasers themselves are ideally suited. Then we have the questions of price versus performance. I mean, some of the high power laser sources are quite pricey. And basically one of the things that fiber laser technology has done over the years is address the cost per watt, which is continuously coming down and enabling more opportunities to take on fiber laser or laser sources for materials processing and welding applications. Quality and repeatability, flexibility, and I guess one of the challenges that I will specifically want to talk about is the joining of dissimilar metals. And really what we want to address now is how these pulse laser sources can address those things above. In terms of the materials that we want to talk about, it's basically limited to relatively thin sections, less than 1 millimeter. I mean, yeah, with a 100-watt laser, there's some expectations that we need to set here. But we can do quite a lot of stuff with these kind of lasers. And what I'd like to do is focus on lap and spot welding. We'll deal with stainless steel and copper in terms of just basic welding processes, and then explore the ability of these nanosecond lasers to weld bright metals and various combinations. And interestingly here you can actually see in the picture lots of different materials, and all of those are basically welded to stainless steel buttons. In terms of these nanosecond pulse fiber lasers, they're little small things. They're like the size of a shoebox, no bigger. They're highly efficient, air-cooled, compact, monolithic in design, which basically means that it's one piece of glass. So there's nothing to adjust, nothing to clean, which basically means they have a long, uninterrupted service life with no maintenance, no alignment, no cooling issues. It's basically fit and forget technology, which is so different to many years ago with solid state technology or CO2s, where you almost needed a scientist to basically keep the lasers running. And also you needed someone skilled in maintenance to make sure that the performance was maintained. Those days are past. I think the advent of fiber lasers means that the reliability and repeatability is second to none now. Many people may be aware of short pulse lasers and how they're generated. Most conventional pulse lasers use what is called a Q switch, which is an energy storage device or technique that basically then discharges the energy available from the laser. The lasers that we generate are based on a MOPA design, a master oscillator power amplifier design, that uses a semiconductor seed to actually generate the pulse, but we then amplify through a fiber train. This gives us some advantages and benefits in giving us greater control of capabilities of the generated pulses. We have a characteristic fast rise, which is different to the Q-switch designs, which tend to be normal in terms of distribution. And that's basically good, as it's quick in overcoming processing thresholds. We also have a lot more scope in terms of the dynamic operating frequency range that these lasers are capable of. And they regularly operate anything from 1 kilohertz to 1 megahertz. We also have user-settable pulse duration and up to, well, in discrete forms, anything from 3 to 500 nanoseconds in terms of full width pulse duration in about 40 different bytes. And these lasers can also be turned into CW sources as well to give you added flexibility. And there are a number of applications where the ability to use pulsing and CW can come into effect. So basically these give the broadest characteristics. And here, the bottom right, you'll be able to see just an example of the array of different pulses with different pulse durations. But what's important to see here is that we managed to keep that high peak. And that's basically part of the application versatility that these lasers offer. In terms of the parametric flexibility, we call it pulse tune. And basically it means that any of the waveforms or pulses, pulse shapes that we have and pulse durations can be used at any frequency. They are optimized for a given frequency to give maximum peak power. And they can be operated below that pulse frequency, in which case the pulse energy remains constant and it's just the average power that will decay or decline. Or they can be operated at higher frequencies, as I said, up to 1 megahertz, where what we manage to do is maintain the average power, but what happens is that the peak power and the pulse energy per pulse decays and declines. And this is basically a key differentiation to basic Q-switch technology. Here we basically have just some more detail in terms of the kind of pulses and shapes and durations that we can have. So basically, top left, we can actually see pulses going from 0 up to about 200 nanoseconds, and there's an inset there, so the other pulses sit inside that, the ones on the upper right, and that shows down to 3 nanoseconds. And then and what's interesting to see is that basically as we shorten the pulses, we don't decay much in the peak power that we can generate, which is so important for coupling into materials. We can then generate longer pulses, where you can see on the bottom left-hand graph, what happens is we're moving the energy around a little bit. So we're losing a bit of peak power, but we're adding it in terms of the length of the pulse. So we're kind of redistributing it a little bit. And this actually benefits several applications, and one of them actually is welding. What we can also do, and this is bottom right, is we can actually detune the pulses. So one of the things that I mentioned previously is each pulse is designed to operate at a critical frequency to give maximum peak power, which is the highest, sharpest pulse on that image. But if we then operate it at a higher frequency, what happens is the pulse energy decays or is reduced. And basically what happens is effectively the full width duration of the pulse remains constant, but we dull down the sharpness of the peak, which basically enables us to tune the laser to the application in question. And that's actually quite important from welding, as I'm about to show you. So I thought I'd share with you an advert we put out back in 2010, where we basically thought that these were pretty much the most versatile types of micromachining and marking lasers. And we knew that they could cut, mark, clean, drill, do all these applications, but one thing that I didn't have on there was welding. So back in 2010, nanosecond lasers were well known for their material removal processes, where the high peak powers were being used to good effect, but not for welding. And that's one of the things that I want to move on to explore now. So it's all about using the right tool for the job. And yes, you are seeing right, there's a coffee pot on an iron. And really what that represents is that we're talking about a paradigm shift in terms of what we believe these lasers can do. It's thinking differently about how to use these lasers to be able to perform welding tasks. So the question we have to ask ourselves is how they do that. The systems themselves are relatively straightforward. Most people will have come across them. Typically, nanosecond lasers are used with scanner-based technologies, which gives high flexibility and control. However, one of the big things for welding people is sometimes the ability to shield and protect the weld from atmospheric contamination. That's actually very challenging if you're operating with a scanner-based solution. You can use these lasers through fixed optic deliveries, through processing heads. It lowers the flexibility and control, but then, if needed, you can apply shielding gases. And these are just some typical data that we would have with 70-watt laser. We'd typically use it with a 163mm f-theta lens, giving about a 40-micron spot size, so with a depth of field somewhere around a millimeter. So it gives you a good operating window that you can actually use in terms of processing. So the other important thing that we need to be aware of is, as I said previously, is we can detune these pulses. So basically, from on the left-hand side, you'll see that a long pulse duration with a very high peak, or a nail and a tail, as I would describe it. And if we basically then just increase the frequency, what we do is we change the P/E, or the peak power to the energy ratio. So whereas in the top graph, effectively, we're showing the maximums, we can minimize this by basically increasing the frequency for a given pulse duration, effectively, getting the same watts, but dramatically changing the shape of the pulses. And the table on the right-hand side just gives you a kind of flavor for the different types of pulses that a single laser can generate. So, for example, waveform 0, the top line there, is typically, for a 70-watt laser, is optimized at 70 kilohertz. It's a 1 millijoule pulse. And because it's a MOPA pulse laser, it's got a high peak, so the full width half max tends to be quite short, but the actual full length duration is actually quite long. And, we can play around with this as well. Obviously, again, as I said, you can actually change the shape, change the peak power, change the pulse energy, change the full width half max, and also change the full pulse width. You've got a lot of levers that can be pulled in developing processes with these laser sources. In terms of process variables, I could spend an hour just talking about the complex interactions, because there's lots of things that you can change that basically controls the heat input. And it's important to balance the spatial and temporal interactions of pulses. And the kind of levers that you have at your disposal are things like speed, the repetition rate, and the pulse duration. And the kind of sources you have, there's also different types of lasers. So you have different lasers with different beam qualities. So whether you want to have a sharp tool or a slightly blunter tool, being truly moded lasers, it's better that sometimes in terms of depth of field as well. And the choice is actually dictated by the application, and we'll show you some good examples of that going forward. At last, we get onto the welding side. So we'll start off with plastic welding. Traditionally, this is a diode or a CW application. The materials, for solid-state lasers need to absorb at 1 micron. As I said, typically a fiber laser or even a nanosecond laser wouldn't be considered for these applications. There are easier ways to do this, possibly. But there are certain applications where spot size and depth of field are important considerations. And that's when the benefits of a fiber laser can come in. And again, the flexibility between being able to use CW or high-frequency long pulses, which is basically a quasi-CW situation, gives you some very good opportunities for making very fine, intricate components with high control and repeatability of the end product. And this is an example of an insulin dispenser made by my good friend Joe Lavotti at OK Industries. And basically, he adopted this laser source for this application because it gave him the flexibility that he needed for this particular application. Other applications, such as soldering, you wouldn't traditionally think about fiber lasers being the source of choice. Again, usually it's diode lasers. But however, one of the things that we're seeing in today's society is miniaturization and heat sensitivity. And this basically may require a finer solution than is offered by some of the other technologies. Here is an example where we had a client that was looking for minimal heat input into a very sensitive component, PCB board, where they needed to minimize the local heating. Even a CW laser was just putting in too much heat and damaging parts that were close by. And so we developed a process where we would spiral in the laser beam using long pulses, again using a 40-watt laser with an M² of 3. In this case, the broader energy profile in the beam helped control the heat input. And we were able to just melt the solder materials, just melt the solder balls on the actual pads themselves. And you can actually see on the lower picture here that solder balls that are actually still on the pad but weren't in the spiral are not even melted. So, moving now on to welding of metallic materials using nanosecond pulses. As we've always said now, we need to use the pulse waveforms and frequencies to tune the parameters, to move away from what I would call vaporization and melt ejection, to basically create an environment where you're actually generating a controlled melt. And this is an interesting set of pictures, because going from left to right, because, you know, what we start off with is a relatively large spot, about 70 microns. And if we just trepan very slowly in a circle, we'll get a horrible oxidized aero-type end result. This is just bead-on plate on stainless steel. But what's interesting is at that pulse regime, we're talking about inputting 70 watts. We're using 1 millijoule pulses. We're having these pulses as greater than a kilowatt. And we've got a duty cycle, because we're talking about these really, really short pulses of basically just less than 2%. So there's more off time, or a lot more off time than on time. And that's the kind of end output that you get. What happens is, as you increase the frequency, you basically reduce the pulse energy, you reduce the peak power, you maintain the average power, and the duty cycle starts picking up. And slowly what you'll see is that you move away from this melt ejection and heavy oxidation to something that's more attuned to a weld. And lo and behold, if you move up one step further to 500 kilohertz, where we've dumbed down effectively the peak power to just over 500 watts, and we're only using 150 microjoules, and we're talking about 15% duty cycle, we can create something that looks like a weld. What's interesting about this is that there is no shield gas, and it is done in a single pass. We can also make lap joints using this kind of technique. And here we've got 304 stainless steel, 150 micron sheets, welded with a 70-watt laser. These are 6mm welds. No cover gas. We get full penetration. And basically, when we pull them apart, it basically fails in the heat effective zone outside the weld. And actually, just by going slightly slower, we can go to 250 micron sheets and increase the thickness. And again, if you have slightly higher laser power, you can probably do a little bit more. One of the other things, well, that's basically just linear processing. One of the other things that is being more commonly adopted within welding, it's not a new idea, because back in the Welding Institute, back in the 80s, I believe, or even late 70s, we're looking at wobbling laser beams to improve fit-up acceptability on welding. So it's not a new technique, but it's a standard feature on scanners. But the ability to wobble the beam through very small radiuses or diameters, you can actually extend or broaden the weld and still create very, very good results. And here, using this technique, we can actually show that we can actually generate bright welds through thickness of materials up to about 0.5 millimeter, which are bright and smooth, and again, single pass, no shield. We have been doing this for a number of years in terms of using these lasers for generating small parts. Coil joining, wire joining, these are applications in industries such as the medical components industry where we need to very much control the heat input. And here is an example of a 50 micron coil where we're welding wire to wire with only a 20 watt pulse laser. And again, the issue here is being able to go to higher frequencies so that we can dull the sharpness of the peak but maintain the focusability and the intensity of the energy to generate a good joint. We can move on, and there's a whole plethora of different kind of applications where this greater precision can be achieved for wire-to-wire bonding. And basically, the choice of laser is dependent on the application. So here are two examples that I'd like to bring to your attention, where one, we're trying to weld or join a braid, a metallic braid, to a wire going through it. And here we need to do some gap bridging. So the ability to have a laser beam with a slightly higher M squared or less beam quality to some people, a broader energy distribution. It also comes with higher pulse energy. That's one of the trade-offs that being able to play around with modes, with fiber lasers gives you. We can bridge that gap. It produces a larger spot, but that's what's required when you're trying to bridge gaps. The example on the right-hand side, however, is joining of two micro wires that are only 12.5 microns in diameter. This particular application is for a micro thermocouple. It's a similar application, but being able to hit that tip, you need a very fine spot, and this is actually achieved with a 20 watt laser, single-moded, truly single-moded, with an M squared of less than 1.3. Are these strong, though? You know, one of the questions you will ask. And the answer is yeah. They produce pretty functional welds. And here we've got an example of a seam that we've created in stainless steel. And pulling it apart, you know, we're getting strengths in terms of this lap seam of about 200 pounds, which is quite reasonable. There's many ways of actually generating. You can either just spiral and do this kind of wobble weld, or you can actually create overlapping spot welds, where we're basically wobbling to create a spot itself. And again, it kind of gives similar results, but it's just a different technique that can be applied. Again, this is very simple using scanner-based technologies, and all of these welds are using no shielding there. So trepanning spot welding, you know, that's one of the big things. We can actually control the size of the spot by trepanning it and control the heat input quite nicely. And this is an application where we were welding 0.5 millimeter stainless steel, and we were getting up to 7 lap welds per second using just a 70 watt laser. In terms of components, yeah, these are the kind of things that we sometimes see. More conventionally or originally were done with solid-state YAG lasers, but these parts are ideally suited to the type of welds that can be achieved using nanosecond lasers. It's basically stainless steels, and just, you know, you've got to be quick to see this. We're going to just hopefully go for a little video clip. It's always a tense moment when you start loading video into webinars. Let's see if it works. Oh, well. some reason, that doesn't seem to want to work. Unfortunately, it was very quick because basically the video would have shown 4 spots and then a seam that's done in just over a second, or under a second, I think it is. Ah, here we go. Slight delay, but so basically this is the staking, so basically doing 4 spot welds. There you go. Blink and miss it. It's very, very quick. And this is basically, like I said, a 70-watt nanosecond pulse fiber laser welding this hub to cap. And again, be careful you blink and then miss it. It literally is very, very quick. And that's generating a weld using a wobble that's generating about a couple of 100 micron depth in terms of weld and a 600 micron width weld, which is basically what the customer in this particular instance was looking for. Okay, so, you know, when we were developing this, what's interesting is one of our applications engineers is an expert in welding, and he actually lives in California. So he was doing this kind of work, and I asked him what else he could weld. And then basically he just sent me this photograph that you can see there, which represents a total cornucopia of dissimilar welding. It's a real smorgasbord of welding. So they've got examples of copper to stainless steel, copper to aluminium, copper to brass, aluminium to stainless, and stainless steel to aluminium. So quite obviously, my question, my retort to Daniel was, you know, but are these welds any good? To which he basically replied with the following photograph, which I thought spoke volumes. So this is basically 150 micron thick copper foil joined to 0.5 millimeter aluminium with 3 1.2 millimeter spot welds, all done in under a second. And basically there it's taking, as you can see by that drum of wire, a static load of 11.7 pounds. So they've actually got some strength to them. So there's some interest here. In actual fact, you know, building on from that, we've done a lot of work that look at the challenges of welding to similar metals. The challenges are the high reflectivity in the near infrared, dissimilar melting temperature, brittle intermetallic structures, and different cooling rates. And the key here is to be able to create mechanical joints independent of these challenges with these 1 micron nanosecond pulses. And again, our focus is the ability to weld these bright metals in a range of material types and combinations. And our focus has primarily been on spot welds, although we do have some seam work as well. When we talk about a spot weld, it's very different to some of the other spot welds that you may have experienced. Because what we do is we basically create these by spirals, like little scales, where we can basically spiral outwards or inwards and basically create a nugget effectively that basically creates a spot. And this is basically made up of millions of pulses, basically. It creates a very good joint with the material. And really, the results are quite interesting because basically, as it says here, it's not always a beauty contest. The results look different, and I think this is the important thing, different to conventional welding, you know, large microsecond pulses. But, as you'll see shortly, they are quite functional. They do the job. So basically, the structure of the visual impact is slightly different, but they have some benefits in terms of speed and the joining capabilities between the materials. So the key thing is basically knowing what these kind of weld properties are. The strengths, for example, tensile strengths. And here we've got some examples of 150 micron copper to copper, 300 micron bronze to 300 micron bronze, 300 micron brass to 300 micron brass, and a dissimilar joint, 150 micron copper to 0.4 millimeter aluminium. And here you can actually see that the tensile strengths are quite reasonable for these kind of foils, and I'm probably fit for purpose a number of joint examples that these kind of metals could be seen in service. What's interesting really is these spot welds are actually metallurgically very exciting. Being a metallurgist by my first degree, when I first saw this, it really did intrigue me. Because basically these spot welds do not show the characteristic forms of conventional pulse spot welds, but resemble more closely multi-staking. And here you can actually see that we're punching into the material through the copper into the aluminium below. And we're actually melting the aluminium, and it's getting sucked back through the hole that you've just punched to basically make a solid material meshing between the two materials. And that's actually quite interesting. And what's interesting to see is that copper is actually injected effectively as well into the aluminium. The interesting thing here is that basically we cannot see the kind of intermetallics that you would normally see at the interfaces. There may be a few examples of some intermetallics, but in the interface zone there does not appear to be any. So when we break them, we see that all of the welds fail in the heat effects zone and in the base materials, and the nuggets themselves remain. We can actually improve the characteristics by what we would call cosmetic passes. So we can actually reprocess the weld with a secondary pass, and that's actually, it's work in progress, but that's showing promise at being able to improve the strength and capability of these welds. In terms of lap seams, we can use the same techniques that we described previously, using wobble welding techniques on joining a range of dissimilar materials. And here again is some joints between copper and aluminium, aluminium copper, stainless steel and aluminium. All things that people are very interested in being able to join. And again, note that none of these used any shielding gases at all. In actual fact, we've actually found that, there's some very exotic and more challenging joints that can be made. And here I have to thank my good colleague or friend, Dr. Jeff Shannon of Amada Miyachi, who let me use this picture where they've used one of our 20-watt single-mode lasers to actually join 100-micron foil stainless steel to titanium. Now, I'm not quite sure why you'd want to join stainless steel to titanium, but I suspect metallurgically it must be quite a challenge. And his statement here is that the flexibility that these laser sources give him enables him to make such joints. In terms of the applications themselves, we're looking at fine welding as a growing market, particularly in terms of the push for miniaturization. We're talking about battery foils, cells, things like medical devices, sensors, and thermocouples are a good example of that. Let's not forget that these lasers are actually capable of doing other things. And this is an interesting application that my colleagues at Trumpf developed, where they're looking at basically structuring metal and then bonding plastic onto it. So you're using the ablative and engraving capabilities of the nanosecond pulses. And then basically you can just put a piece of plastic on there, a thermoplastic, and then basically turn it onto CW, pass over that, remelt it, it will flow into the grooves, and again you get a strong joint. Other applications are things like cleaning with nanosecond pulses. The high peak power short pulses can be very good at selectively removing material pre-processing. For example, the selective removal of zinc pre-welding. And actually, this is just an interesting example. Here you've got a piston head, and this was sent in to us from someone from India that basically wanted us to try and remove the carbon, the coating that was on the piston head. And what's interesting is with these nanosecond pulses, we can actually remove totally all the carburization, all the hydrocarbon, all this kind of debris or gunk that's been on these piston heads, down to the metal without removing the machining marks. You can still see the machining marks. We're very selective in what we can do. And then again, so that gives us the flexibility. Let's not forget that these can cut, weld, mark, and do all those other applications, which gives benefits in terms of combining processes, and particularly in applications where you want to do combination processing, such as cutting, welding, then marking. These can be done, particularly on micro devices, small devices with nanosecond pulse lasers. In terms of conclusion, what we have here is something that provides efficiency, low power, low cost solution, capable of welding thin section materials. We have a lot of quality to offer in terms of reliability and repeatability and control of these laser sources, and their utility is good, being able to deal with bright and dissimilar metal combinations. So I hope you'll agree with me that, you know, nanosecond lasers are not just micro machining lasers, they are micro welding potential laser sources. 2 slides to go, guys, so we're almost there. So literally, I just wanted to finish off on the fact that we have different types of lasers, and it's quite important to match the laser to the kind of application that you have, whether you want precision heat input, dealing with bright metals, and depth of penetration, or whether you're dealing with materials that are better off with a slightly broader energy distribution. And, you know, we have different laser sources that would be optimized for, or are optimal for different types of applications. So that concludes the webinar. So thank you very much for your attention. For further information, please feel free to contact me directly. My email address is there. Or if you want a commercial discussion with some of my colleagues, you can use our sales website. And I'd like to conclude with a special thanks to Daniel Capistano in our Santa Clara office, who did most of the grunt work. I just get the benefit of being able to present it. And that's basically about the versatility of these very small shoebox-sized lasers that can do so much, including welding. Thank you.
Thank you very much, Jack. Now it's time to turn to our audience who have been sending us a number of questions. Jack, if you would, I'm going to try to zip through them to get as many as we can get into time allowed. First question up is, for fine wire welding, do you need to apply a mechanical bonding force over the fine wire?
Oh, right. Okay. Fixturing of these kind of fine wire and fine welding applications is very important. Sometimes they need to be in intimate contact. You don't always need to be pushing them together. But basically, the fixturing and jigging is the headache that can take a lot of time and effort in getting right. But once you've got it right, the laser welding part is relatively straightforward, or it can be straightforward. So I think the answer to the question is they have to be in intimate contact. You don't necessarily need to be pushing them together. That's actually almost impossible with fine wire.
Okay. What should you do about the heat-affected zone failure? Post-heat treatment, is it needed?
It's not something that we've basically really got into. We basically have been doing tensile tests to just ascertain the strength of the welds. Many of the welds that we're looking at are actually or are being placed in situations where there is or to minimize the requirement for strength. I guess in some instances, post-processing heat treatment could improve that situation. And I think, one of the things that we did do is we have started looking at post-processing by primarily improving the surface finish. And we found that did give us improvements, or has given us improvements. It's work in progress, but it shows some potential.
Okay. What is it about the nanosecond pulses that gets around the challenges of dissimilar metal welding?
I think one of the things that hopefully you saw when I got very excited about the metallurgy is that basically you've got this situation where you're multiple staking. With conventional welding, where you have melt pools that are molten for a reasonable amount of time, you get growth of these intermetallics at the interfaces. And that's basically because there is a very visible weld that is basically typically from a single pulse or consecutive pulses. The weld line, the joint between the weld and the base metal is very distinct. What we found is that by using this nanosecond pulsing technique, we're breaking this up. And so we don't see this continuous form of this brittle intermetallic layer. Again, it's early days, but preliminary work that we've done is extremely promising, and a lot of people raised their eyebrows at the potential of this.
Jack, one of our guests asked, if I have an aluminum-clad stainless steel, is it easy to weld to itself? I want to be able to weld this into a tube.
We haven't tried that, and if I'm very honest, we haven't done a lot of butt welding with this technique, and it would depend obviously on the thickness, but it's something that I'm sure we would be prepared to have a go at. But we've found that basically it's more tolerant to the material combinations that we're seeing, so it's something that might be worth trying.
This one is going to challenge you a bit. Why do you think that the stainless steel welds do not oxidize as the rep rate increases? Is it simply lower heat input?
I guess it is basically controlling the amount of heat input, and basically it's about the disruption that's being generated at the surface as well. So you're creating more of a melt, and there's more stability being generated. So what's happening is you're getting less peak power, you're getting less vaporization, you're getting less turbulence on the surface. And that's probably creating a situation where you're getting less oxidation.
A general question, can you please share some of your experiences about the fatigue performance of laser welded joints?
Right, okay. One of the things about today's welds is that we haven't done any fatigue work on the kind of joints that we've been discussing today. It tends to be in applications where they're not being used in fatigue. I think that's something for the future. In terms of fatigue for other types of laser welding, it's an ongoing work. It is very dependent on the kind of materials that you're looking at. And basically heat inputs, geometry of welds, geometry of parts, and also the shape of the weld nuggets, all of these sorts of things, undercut, all affect the fatigue properties of welded joints. It's something that the industry or welding engineers could talk for hours and hours on, and you need to look at specific examples to be able to give more concrete comment and advice.
Jack, this attendee asks, can pulse tune be used independently from the laser source itself? For example, if one wishes to use a specific laser power laser for imaging, would it be possible to integrate the system to generate laser waveforms? If so, what are the basic requirements?
I honestly don't know the answer to that. So basically, the waveforms themselves are internally generated as part of our control of the seed itself. How we could control that externally, I wouldn't know.
Okay, I'll make it easier for you. How about depth of weld penetration, maximum thickness of two metal plates that can be welded with nanosecond pulses?
Okay, so that's an interesting one. We've actually got through a millimeter in aluminium in the last few days. So that gives you an example of, and that's a laser that's less than 100 watts of average power.
Okay,
That
copper
gives
to
you
copper. Excuse me. Copper to copper, copper to aluminum, and aluminum welds are all used in battery construction. Resistance is important. So do you have any information on weld resistivities?
Yes, we have. There have been some resistance tests, and the resistance capabilities of these are extremely good, and of a similar order of magnitude to other welding technologies.
Is the order in which the different materials are important? For example, aluminum, copper to 62, aluminum 1. Is it important about the type of material? Answer is obviously yes.
It hasn't appeared to be. It's interesting that basically you can actually weld pretty much, or join pretty much anything. I won't say anything to anything, but the kind of materials, and the materials that we've looked at are things like brass, copper, stainless steel, aluminium, bronzes, and we kind of almost be able to mix and match and join pretty much anything to anything. Again, some works better than others, but it depends whether you need functional strength in these kind of joints, or whether you just need them to be coupled together. And again, this is we could spend years and years evaluating the different dissimilar combinations. But I hope what I've managed to show is the sheer diversity of materials that we have done. So, for example, we basically showed here that we can do aluminium to copper, stainless steel to aluminium. So we've basically, in copper to aluminium. So we've basically looked at doing things one way and then the other, to show the differences in the combinations that we can do. We are working now with universities to broaden our knowledge about this, and the next year or so will no doubt bring much more technical data that we will be sharing with everybody.
Fairly general question, Jack. Did you see any micro-cracking in welds?
We do see some defects, weld defects and porosity resulting from some of this welding technique, in terms of the trepanning spot welds, and optimization of the parameters and heat input. Basically, we try and minimize these, but we haven't specifically been looking for cracking as such. We haven't.
Okay. Is there a minimum pulse duration below which welding is not possible?
I can't say that we've actually tried. We tend to use the slightly longer pulses, which tend to be in excess of a couple of hundred nanoseconds. A few hundred nanoseconds seems to work well. We haven't got. I don't think the three nanosecond ones. I don't believe we'll be able to weld with.
Excuse me for interrupting. So, is your equipment able to weld metals and create a seal to avoid the leaks? Hermetic sealing, we're talking about.
I suspect they will be able to, yes, in certain instances. Because
okay,
if you see some of the microstructure, hang on, I'll just pan back to one of the slides. We can get pretty good looking weld nuggets. Hang on a second, actually. So, for example, where we're showing this particular joint here, we can get pretty good. So this is a lap weld where you can see halfway through the image on the left-hand side is the joint. It's pretty continuous. So I would suggest that on that basis we should be able to do hermetic seals.
Okay, you mentioned that no sysgas or cover gases were needed for many of the applications. Is this true in titanium welding?
That was a picture that I got from one of my colleagues, Dr. Jeff Shannon. I'd have to ask him that. I suspect that with materials as reactive as titanium, you will most probably want to apply some form of shielding.
Welding thin foils on the order of 10 to 20 micrometers, what would you suggest? High frequency and low pulse duration, or CW?
We've had very, very good results with high frequency, long nanosecond pulses. And one of the last slides that basically suggested that a broader energy distribution actually benefits those kind of applications. So you don't want to use too sharp a tool for joining those very, very thin foils.
Jack, can you weld through a glass fixture to the parts that are held together underneath?
I suspect you will be able to. You know, one of the things that glass does is basically transmits the wavelength of light in question. And if you have foil underneath it or material underneath it, it absorbs and it will melt. So I haven't tried it as such, but I would have thought that it would be possible to do something like that.
Jack, I'm not sure. Did you mention any applications for welding titanium to titanium?
No, not at all.
And no experience?
No, not with nanosecond lasers.
With the ability to post-clean the weld area, is there any need for shield gas using this technology?
Well, the question will come is whether the oxidation is embedded into the weld metal, because basically if you're surface cleaning that, you won't be able to get any embedded or deeply embedded material out. So our cleaning passes have basically been more about remelting and changing the structure to some extent on the surface. So it's like a remelting pass, rather than just removing oxide.
Jack, the last question that we have time for, are you able to use this laser to weld platinum and nitinol? I
can't say that I know that is the case, but I suspect that it would be something that would be worth trying.
Okay. Thanks, Jack. And attendees, I know there are several questions that didn't get answered. Some of them were very specific, and Jack will be pleased to answer these himself individually after we're online. On behalf of Industrial Laser Solutions and Penwell Corporation, I would like to thank today's speaker, Jack Gabstel, Vice President of the Pulse Laser line at SPI Lasers, who are our sponsors. But today's presentation, Welding with Nanosecond Pulse Lasers, I think we all gained a nice perspective on a new technology that's going to be available to us in the coming days. This presentation will be archived within 24 hours and can be accessed from the home page at www.industrial-lasers.com. A reminder email message for the archive will be sent to all registrants, complete with a direct link to the archive. I invite webcast attendees to follow the technology presented today in the pages of Industrial Laser Solutions magazine, where ultra-fast pulse laser processing will be a feature of many of the issues in 2016. You can register for a free subscription on www.industrial-lasers.com. We thank you for joining us today and look forward to serving you with future webcasts.